So this is Complex Analysis, Math372, Lecture 25. We've talked a lot about the difficulties of switching sums and when it is justified. So this is a clip from when Cameron was about 2 years old. This is another way to justify interchanging summations. We seem to have completely lost all volume. Let's try again. All right. Now that's the best volume I can get, sadly. All right. So it really isn't that hard to learn how to switch sums. Justifying that is a little bit different. Okay. So what we're going to do today is we're going to finish off the stuff where we were doing Fourier analysis leading up to Poisson summation. So we proved Bayes' theorem. If f is continuous, then f star Tn converges to f, I'm sorry, star Fn converges to f pointwise. And this is terrific. So what does this mean? So it means that we have an incredibly good way of approximating our value of f. We look at this nice sum, and this sum is going to be a bunch of weighted Fourier coefficients. I forgot to check if it was n over big N or an absolute value or the square of that. The thing is, for all practical purposes, it doesn't matter if it's squared or not squared. I'm quickly trying to take a look and see which way it was. No, I forget. So I will, in the interest of time, I'll just say, so it's either the sum n goes from minus n to n of 1 minus absolute value of n over n, f hat of n, e n of x, and maybe this was n squared over n squared. Doesn't really matter. What's great about this is converging pointwise for every x. This is getting closer and closer and closer to the value so long as f is continuous. A nice consequence of this is a theorem of Weierstrass. So we saw Weierstrass when we did the Weierstrass product representations. You can represent any function f which is continuous as a sum of polynomials. How do you do a sum of polynomials? Well, for each of these, you can write it as sine and cosine. You can then Taylor expand the sine and the cosine. And what you can say is, well, for each one of these, I can just make sure the approximation is really good. So all continuous f can be pointwise uniformly approximated by a polynomial of finite degree. And all you need to do is, if you're already within, say, epsilon over 2, then for each one of these, approximate the sine and the cosine so that you're within, say, epsilon over 1,000 times big N. And that will be so much that even when you add everything together, it's still going to be close. So because we can approximate each of these well with 1x, x squared, x cubed, we can then approximate the original function. What if we didn't want to use the weighted series? What if we wanted to use just the original Fourier series without the weights? Well, it turns out if our function is differentiable or almost differentiable, it's close enough. So let's look at f star dn. And the question is, will this converge to f? Sadly, not always. But if f is continuously differentiable or almost so, it will converge. And the argument is extremely similar. We again subtract 1 by looking at f of x minus f star dn of x. This is going to be f of x minus f of t minus x minus t dn of t dt, integral from minus a half to a half. And the Dirichlet kernel integrates to 1, so I can just multiply by the integral from minus a half to a half of dn of t dt. And so I'll just get f of x minus f of x minus t times dn t dt, integrate from minus a half to a half. Okay? Well, what we did before is we said, well, look, when t is close to 0, this is small by continuity. And then when t is a little bit away from 0, because this is an approximation to the identity, this is small. Sadly, we can no longer do that because this is not an approximation to the identity. Now we use the fact that we actually know something about the Dirichlet kernel. And this is where I hope my memory is good enough, but if not, I hope your memories are good enough. This should be like the integral from minus a half to a half of f of x minus f of x minus t. dn of t was the sine of, I believe, 2n plus 1 pi t over the sine of pi t. And I think there was an n down here. Or no, I don't think there was an n. I think it was just like this. I think this was the Dirichlet kernel. Okay? How do we handle this? And why do you think differentiability is now important? Okay, and so what would I want to integrate by parts? So where's the troublesome point? See, as x gets closer and closer to 0, this is getting large. This is blowing up. Let me just double check and make sure I have the Dirichlet kernel correctly. Yep. Or approximately the same. Up to, okay, good. So the problem is this ratio could be really bad near t equals 0. Because near t equals 0, I could get like a 2n plus 1 pi t over pi t that could be blowing up like n. However, how large can the sine be? 1. So in terms of blow-ups, the blow-up isn't really so much coming from this, it's only coming from this ratio. I don't want to divide sine by sine. Where should I move the sine pi to? I'm sorry? To the what? To the f's. Or better yet, what would you love to have above sine pi t that would have a really nice limit? What would be great to have above the sine pi t? T. Or if you want to be fancy, instead of having t, you would have pi t. So let's just multiply by 1. Minus a half to a half, f of x minus f of x minus t over t. Well, I'll put the pi over there. Then I'll have a pi t over sine pi t sine 2n plus 1 pi t dt. And now, if my function f is differentiable, this limit is well behaved. This limit is well behaved. And so if f is differentiable, this is nice if f is differentiable.
Which
yes?
limit are we taking here?
The limit as t goes to 0. Away from t equals 0, there's no problem here. But when t is close to 0, the problem is this is exploding. And I don't want the contribution to be too large. So the nice trick is you multiply by 1. This is well behaved. This is well behaved. And now this is bounded by 1. And in fact, if you want, you can look at this as the imaginary part of e to the pi n plus 1 it. So what this is really is this is the imaginary part of a Fourier coefficient. It's the imaginary part of the Fourier coefficient of this function. So we have the imaginary part of g hat of 2n plus 1. Where g of, we've got to be careful, we'll call it g sub x of t is going to be f of x minus f of x minus t over pi t over sine pi t. That's a nice function. What do we know about the Fourier coefficients of a nice function? They converge to, we have Bessel's inequality, that the sum of the Fourier coefficients is less than the L2 norm. So by Bessel, sum of gx hat of n squared is, less than or equal to the L2 norm of gx of t squared. I guess I'll do squared dt. And so the only way that this sum can be less than the integral is if the summands are going to 0. So if we know that this function is integrable, if it's square integrable, then we're fine. And so we just need enough assumptions here on f that this will all make sense. And then what we would get is for fixed x, this will go to 0, and you will have convergence. Then it would be nice to have uniform convergence and have this independent of what's going on for x. That's much more work. But right now, this is enough to show that the Dirichlet series will converge. We actually don't need this to be differentiable. So how many of you have heard the phrase Holder or Holder continuous? So if you take the absolute value function, is the absolute value function differentiable? No. But it's not differentiable in a really good way. If you take the right limit, you get 1. If you take the left limit, you get -1, unless I flip my signs, in which case it's -1 and 1. But the ratio, the quotient for the absolute value of h of x minus h of 0 over x, it's bounded by 1 in absolute value. So we don't really need this to be differentiable. We just need that this is bounded in absolute value. And so with that assumption, all of this argument would work, and we would actually have convergence of the absolute value function. So it's always nice to see how far can you push this. There's some people here who might be looking at PDEs. And it's always a game of what is the weakest condition you can impose and still get something meaningful. We now have pointwise convergence of Dirichlet series. Okay. All right, so now the question is building up to Poisson summation. So I would like to turn Bessel's inequality into an equality. And again, a lot of it can be a function of what is the weakest set of assumptions you want to work with. If I'm willing to assume a little bit more about differentiability, I can use Dirichlet's theorem. If I don't want to make assumptions about differentiability, I use Fayet's theorem. And the only real difference is this weighting of coefficients. And if you look, what can you say about the Fayet series of f minus the Dirichlet series of f? Well, if you look at that, they basically, this is going to be less than or equal to the sum, and goes from -n to n of absolute value of n over n f hat of n, something like this. And again, maybe these are squares. I forget. I should really know better, but it doesn't matter. So we have a sum like this. We'd love this sum to be small, right? What will make this sum small? And in what ranges of n will that make things small? So in different ranges of n, different things might kick in to keep this small. So can someone tell me a range for little n where this is small?
equals 0.
N equals 0, good. So let's go a little bit more than just n equals 0. If little n has what relation to big N? Yeah, if little n is like at most square root of n, this would be like a 1 over root n. Remember, f hat of n is the integral from minus a half to a half of f of x e to the negative 2 pi I nx dx. So if I take absolute values, the absolute value of this is less than or equal to, I'm now going to lose all the oscillation. So the Fourier coefficients are uniformly bounded, independent of n, by the L1 norm of my function. So all of these f hats are bounded. So if little n is less than square root of n, the contribution is small. Unfortunately, about how many n are less than square root of n?
1 over n.
I'm sorry?
1 over n.
No, how many little n are less than square root of n? In absolute value. I'm sorry?
N.
All right, let me write this down. How many n are at most square root of n in absolute value? 2 square root of n, or actually 2 square root of n plus 1, but I don't really care about the contribution of the 0. So if I say, well, let's take little n up to square root of n, then each one of those gives me a contribution of 1 over square root of n at most. Unfortunately, I have 2 root n of them, and so their total contribution sadly could be of size 1, and that's not small. So it's not a bad idea to go all the way up to square root of n, but that's a little bit too far. So what should you go up to? So you could go up to log. That would work. You could go up to n to the 1/2 minus epsilon. Do absolute value of n less than or equal to log n, or n to the 1/2 minus epsilon, or n to the 1/4, anything like that. And then the contribution up to those pieces is going to be small. So this is a really good technique in analysis. I'm not sure if you've seen arguments like this before, where you break things up into 2 different types, and in each one of them, you have to apply a different technique to understand it. And so when little n is small, I'm going to win because the ratio n over n is small. Now, if we actually had those as squares, as n squared over n squared, then going up to square root of n would have been fine. So for this part of the lecture, that would have really helped if I had known that that was correct. But it's not going to really matter. So what we can do is we can break it up into 2 pieces. So this is going to be less than or equal to the absolute value of n less than or equal to, let's say, n to the 1 minus to the 1/2 minus epsilon, n over n f hat of n. And then we'll have a plus a sum of n greater than or equal to n to the 1/2 minus epsilon, n over n f hat of n. Okay? Now here, we all agree that we can make this small. Now for this one, what can you tell me about n over n? Could this be very large? How large could n over n be? 1. So n over n could be 1. And in fact, most of the n's are going to be very close to big N in terms of size. So unfortunately, the n over n is no longer going to give us decay. But what do we know about the sum of the Fourier coefficients? They converge. Well, do we know that the sum of the Fourier coefficients converge? What do we know converges? We know the sum of the squares converges. Right? So if we want this to work, we would need just a little bit of extra support. We would need to somehow have an argument where this is coming in with squares. It's possible I have a sequence whose squares converge, but the sequence itself doesn't converge. Imagine the sequence 1 over n. The sequence 1 over n diverges, but the sequence 1 over n squared converges. So unfortunately here, this would not be enough to get convergence. it would be close. So what we would need is we would need a slight modification where instead of this, we were somehow looking at something where this came in as a square. So again, what I want you to get from all of this is just the idea of how you attack problems, how you look for convergence, how you look for decay, and then what you need to do to make the argument rigorous. So if I'm just looking at a difference like this, I'm in trouble. But if I look at a difference like this squared, then I would have squares coming in here, and then I would be okay. We can't use the old trick we did before, of f hat of n is less than equal to f hat of n squared plus 1, because unfortunately that plus 1 is going to have a very large sum. Even we're only starting at n up to 1/2 minus epsilon. It's going to be a huge sum. Going from n to the 1/2 minus epsilon all the way up to n, it's basically the same as going from 1 to n. You're throwing away square root of n out of n. Insignificant. So an approach like this would fail. It would only work if you could somehow get squares coming in. And it's possible to do these arguments and get the squares coming in. But it's telling us we're not going to be looking at point-wise differences. We're going to be looking at like L2 differences, integrating against each other. And when we do something like that, then we'll be okay. And then we'll have a squares. So again, I'm just trying to give you a sense of what goes on and why the different levels of convergence mean so much. Okay. So let's finally get to the Poisson summation formula. So this is the big result. Hey, they fixed the clock. It's good. They didn't put on a new glass piece, but okay. All right, so the Poisson summation formula. Let's say f hat, and f double half are nice. Then the sum, n goes from minus infinity to infinity, of f hat of n equals the sum, and goes from minus infinity to infinity of f of n. And here, f is a function from R to C. So it's not from 0 to 1. So f hat is now the Fourier transform. So f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. This is extremely similar to the Fourier transform when we were on the Fourier coefficients on minus a half. The only difference now is we're going from minus infinity to infinity. To maximize confusion, we use essentially the same notation for both the Fourier transform on R and the Fourier transform on minus a half. The way you should look at it is we're talking about the Fourier transform, and we just change which set we're looking at. Oh, come on, Kayla, that was perfectly tossed. It landed right in front. Kayla needed to throw something out, and so I put on just enough force to get the garbage can to stop right before her and not hit her. Sadly, it was not recorded. No, I should not make it hit her. No. All right, so we look at f hat like this. And nice means that f of x is less than equal to x 1 over x to the 1 plus delta, delta greater than 0, x is large. So what it means is my function has reasonable decay at infinity. So the function 1 over x diverges if I integrate it. But 1 over x to the 1 plus delta will converge. So what I'm saying is I want my function f, its derivative and its second derivative, to be nice, continuous functions, differentiable functions, and I want their derivatives to decay at a good rate. In any finite block, I don't really care what's going on. But in the limit, I want decay. I want so much decay that I can integrate. Okay? Can anybody give me a function that would be nice? It has at least 3 names. So this function has at least 3 names. The Gaussian, the bell curve, the normal distribution. This is your go-to nice function. 1 over square root of 2 pi e to the negative x squared over 2. That would be the standard normal. it really decays. It decays faster than exponential. So we're not really worried about that. Okay. Now, the notation is sadly a little bit annoying here. So little f is our function on the real line. So consider the following. We just spent a lot of time working on Fourier analysis on the interval minus a half, or the interval 0, 1. And now I'm giving you a function defined from R to C. So this is annoying, right? All that work we just did, I can't use, because I have a function from minus infinity to infinity. What would we love to do to this function from minus infinity to infinity? Yes?
Shrink it so that it's only on.
Somehow shrink it down. Well, it's going to be hard to shrink something from minus infinity down, because if I rescale it by a factor of 1 over quadrillion, it's still from minus infinity to infinity. What we want to do is we want to come up with a new function that's related to our original function that lives on minus 1/2, or lives on 0, 1, something like that. And so, again, you will not be tested. You will not have homework problems on these things in particular. This is meant to show you what is out there in mathematics, to give you a sense of what are the techniques, what are the theorems, what can we do. Okay? And to just give you a sense of the thought process. We're going to define a new function. F of x is the sum, and goes from minus infinity to infinity, of little f of x plus m. What's nice about this function? Yes?
Every point on the real line in some way contributes to some point in any interval of length 1.
Okay, you're close. What kind of function is this?
Periodic.
It's periodic. What's the period of this function? What is it? It's 1.
Oh, yeah.
We're summing over n. N is gone. It's 1. F of x plus 1 is f of x. Because if you just replace x plus 1, well, then just let m equal n plus 1. So as n ranges from minus infinity to infinity, so does n plus 1. We now have a periodic function on 0, 1. Isn't this wonderful? What's the one potential problem? Yes? Yes, that's a real problem. This function may not exist. So does this converge? When I was in college, when you met, this was before everybody had cell phones, so one of the questions you asked people was not, what's your phone number? You'd always ask, what's your name? Where are you living? Where are you from? What are you interested in studying? There's like a standard series of 5 questions you go through when you meet people. Okay? When you meet a function, there should be a couple of standard questions you ask. Hello, how are you doing? Do you exist? That should be your very first question. After the function exists, what should you ask? Are you continuous? Then what should you ask? Are you different? And you go, hey, wait, we just met. Okay, so you have a sequence of questions you go through. Okay? And you really want to know the answers. But if the function doesn't exist, does it make sense to ask, are you continuous? There is the story of a math grad student who proved results about a certain class of functions for their thesis. I've never been able to confirm this, and then it came out a few years later that the only functions that satisfied these conditions were the constant functions. And most of these results were already known about the constant functions. So you want to understand, well, what's in your space? So let's see, does this exist? So do you think it will always exist? Or do you think some conditions might be necessary on little f to imply existence?
Well, certainly that kind of being nice is sufficient.
So that's going to make these sums converge. So because of this condition, the sums will converge. What I want to do is I want to show you a situation where it will not converge. Imagine the following. And so one of my real analysis professors, who actually taught me first semester complex analysis, Peter Jones, was really good at highlighting that in real analysis, if you remove a condition, it should be wrong, or the proof should be much harder. You want to get to know counterexamples. Let's imagine that the function doesn't decay. So if I tell you that the integral from minus infinity to infinity of f of x, dx equals 1. So it's a finite integral. And if you want, let's assume f is non-negative, so I can drop the absolute values. We'll assume f is greater than or equal to 0. What does this tell you about the values of f as we go far, far, far down the real line? So we all agree that if the function integrates to 1 and it's non-negative, the values must be decreasing. No. Try again. It does not imply that the function must be decreasing. Well, it integrates to 1. How many of you have seen The Princess Bride? Okay. What was true about the dread pirate Roberts when he was brought to see the Max the Miracle Man? Was he dead? If you've seen The Princess Bride, you should know. Was the dread pirate Roberts dead? No. Can't do anything with dead. What was he? It's a technical state. Come on, this is American culture. You got to know this. This is disgraceful. Watch The Princess Bride this weekend. Kim, what was he? They didn't use the word alive. Dead, there's nothing you can do except put him out because he smells bad. He's only... Oh, that was your chance, Kim. Nobody remembers? Mostly dead. He was mostly dead. And mostly dead means somewhat alive.
Exactly. That's why I said alive.
No, but he's only somewhat alive. He's not alive. It's a small technical difference. So if the function integrates to 1, it's mostly going to 0. It doesn't mean it goes to 0 everywhere. It just means the set of points as x gets larger and larger and larger, where the function is getting above epsilon, is getting smaller and smaller and smaller. So again, this is why I want to take these detours. I really want to review some of the stuff you have from analysis, or introduce you to some things if you haven't seen them in analysis, and give you a sense of how to attack problems like this. Imagine this is what's going on at n. Here is n plus 1 over n to the 2017. Here's n minus 1 over n to the 2017. And I'm going to take a triangle function like this of height n. What's the area under this piece? The area is going to be what? Not half n squared. It's going to be 1 over n to the 2016. The height is n, and the base is 2n over 2017. I'm moving 1 over 2017 to the left and the right. So the area is n over n to the 2017. Because I have twice of that, and then I have half because it's a triangle. So this area is basically 1 over n to the 2016. And so over here at n minus 1, I would have a slightly smaller triangle. And at n plus 1, I would have a slightly higher triangle. So as I go further and further down, my triangles get higher, and their width gets smaller. And if you look at what you would get, is you would get the sum of n of basically 1 over n to the 2016, which is finite. So here, and so if I want to integrate this function, I will get a finite value. So here's a function which is integrable, and it's not going to 0. In fact, I could integrate the square of f, and it would still be finite. The cube of f. I could probably integrate f to the 2014th power, to the 2015th power. But if I did f to the 2016th power, then I would have 1 over n, and it blows up. So here's an example of a function whose first 2015 powers are all integrable, but its 2016th power breaks down. You do not go to 0. Why is this so different than sums? If I give you a sum that converges, the terms go to 0. Why isn't it the case for a function? What's the difference? You can change the width. So for a sum, each piece of the sum has a weight of 1. Whereas for the function, if I want to make the function large, I can just keep shrinking where that function is positive. And I can make those weights as small as I want. So it's not like I have a weighted sum. Okay, well, if I have a weighted sum, then the terms don't have to be getting small if the weights are getting damn small. That's a technical term in their readings, if I didn't hear that. Okay? So it's really important to get a sense of when things exist. So I'm not going to go through the analysis proofs, but if you do the fact that little f is nice, it will show you that this function converges. And you can see that it should make sense because when you actually execute the sum, you're going to be getting decays, so the sum will converge. What do you think is also true about this function big F? So big F, we know it exists. So 1 exists. What should we ask next? If it's continuous. What do you think? Yes or no? Given that I'm lecturing on this, and I really need continuous functions, it's quite likely that this function is continuous. What do you think might be necessary to show that this function is continuous? But we've got to be careful because we need decay. So assuming that little f decayed was enough to get existence, what do you think I might need to show existence of the derivative? That maybe f prime is nice. So if people want, I'm happy to take more time to go through this. Do people want to see a proof of continuity? Okay, I'm seeing some people going like this. So let's show that's continuous. There's a lot of good techniques here. And then as I'm erasing, what do you think the next question will be? If it's differentiable. And the answer will also be yes. And what do you think will be helpful to prove differentiability? The second derivative. So let's look at f of x plus h minus f of x. So this will be a sum and goes from minus infinity to infinity of f of x plus h plus u minus f of x. Are we able to do this? Yeah, the sums converge, so this is okay. Yes.
Shouldn't there be an n somewhere in there?
Oh, yes. Thank you. F of x plus h plus n minus f of x plus n. How might you approximate this difference?
You can multiply by h over h and get the difference quotient for the derivative.
Okay. But we fixed h right now.
Oh, okay.
Right? Now we could then try to take a limit as h goes to 0. What do you think is going to have to come into play? So what do you think we're going to have to use in this argument to show that it's continuous?
You could use like a second order Taylor approximation.
We could use a second order Taylor because we're assuming things about f prime and f double prime, but we can actually just use a first order. How many of you have ever watched Friends? Okay. Almost every episode of Friends begins the same way in terms of the title. So this is your second chance for pop culture extra credit. The one with. So when I teach the proof of the fundamental theorem of calculus, I titled the lecture, The One with the Mean Value Theorem. And we just use the mean value theorem again and again and again and again. The mean value theorem is one of the most important results we have. Whenever you see something like this, you should be thinking mean value theorem. So I'm going to say this is the sum of n less than or equal to big N, and then by the mean value theorem it'll be f prime of x plus h plus some point c of n, where c of n will be between 0 and 1. And now what's the, I'm sorry, it's f of x plus n plus c of n, And then what's the distance between them? H, plus a sum of n greater than n of f of x plus h plus n in absolute value, plus a sum of n greater than n of f of x plus n in absolute value. So the terms when little n is small, I'm going to use the mean value theorem. And the terms where little n is large, I'm going to just approximate the difference by the sum of absolute values. The reason is the sums converge. So if n is really large, these two pieces are negligible. And what's nice about all these pieces here? What's nice about all these pieces? What do they all have in common? They're multiplied by h. So we're trying to show continuity. So we can make these two small by choosing big and large. And again, I strongly urge you to go through and put in the technical details. Because the functions have nice decay, these sums are bounded. We can make each one of these less than epsilon over 3. So this will be less than epsilon over 3. These will be less than epsilon over 3. And then this piece will be h. And now f prime is bounded. So there's going to be some value here. And then the number of terms we have is, like 2n plus 1 times the bound for f prime plus epsilon over 2 epsilon over 3. And if I want this to be continuous, I want this to be less than epsilon if h is less than delta. So if I just choose h to be less than delta, which I'll take to be less than 1 over 2n plus 1 times b plus 1, and I'll do like 1/3 up top, then the whole thing will be less than epsilon. I put in the plus 1 just in case b happens to be 0. I don't want to divide by 0. If b happens to be 0, okay, what would it mean for b to be 0? Okay, it means the first derivative is always 0. Okay, there's really no need to do much of this analysis. The function f is constant. Since the function decays, what is the only function it could be? 0. All right. But it's good to get into a habit like this. Just put in a little extra plus 1. So what this shows us is that if we take h to be sufficiently small, we can make this less than epsilon for any epsilon. We have freedom in terms of where we choose big N to be. And this proves continuity. Now we need to just prove differentiability. Well, we get differentiability by showing that, oh, good Lord, f of x plus h minus f of x divided by h. Do we have any candidate for what the derivative should be? Term-by-term differentiation. So you now have a candidate for term-by-term differentiation. You then subtract the two and show that as h goes to 0, they converge. What do you think you might need to use again? The mean value theorem, the one with the mean value theorem. And what do you think is going to emerge now when we use the mean value theorem again? So here we use the mean value theorem and we got f prime. When we use the mean value theorem again, what do you think we'll get? F double prime. And now you can begin to see where these conditions come from. I am not trying to give you the easiest, no, I'm sorry, I am trying to give you the easiest proof. I am not trying to give you the most general proof for the most general function. When I was an undergraduate, I would have been pissed if I was in your place right now. I did not really know math. And I wanted all my theorems proved in the greatest possible generality, and I was always upset when extra assumptions like this were put on. I now do things other than homework problems from textbooks. And in what I do, my function's actually infinitely differentiable and smooth and rapidly decaying. And so conditions like this, oh yeah, that's fine. I don't care at all. I'm happy to assume those. It's sometimes nice to know how far you can push things, but in practice it often doesn't matter, and in the cases you're looking at, you'll be fine. All right, so now we know that our function exists, and our function is differentiable. Everything is good. All right. So now here is the proof of Poisson. So f is continuous, f is differentiable, f is periodic. So we know f star Sn, f star Dn converges pointwise big F of 0 is the sum n goes from minus infinity to infinity of f of n. Ah, that is half of what we want to show. Right? So now if we look at, f star dn, that's, Sn of f. So now all we have to do is figure out what is Sn of f. And so it's going to be really close coming down to the clock. The goal is to just give you a sense. But of course, at this point, you can figure out what Sn of f should be. So Sn f of x is going to be the sum, absolute value of n less than or equal to n, of big F hat of n e to the 2 pi I nx. What point do you think we're going to want to evaluate this at? We're going to want to evaluate it at 0. So then we get Snf of 0 is just the sum n less than or equal to n of f hat of n. And then we just take the limit as n goes to infinity because it's converging pointwise. We'll have a whole sum. So now we just have to connect this to what we have before. So now we have f hat of n is the integral from 0 to 1 of big F of x e to the negative 2 pi I n x dx. Right? But we know what f of x is. It's the integral from 0 to 1 of the sum, I'll use a different letter, m goes from minus infinity to infinity, of f of x plus m e to the negative 2 pi I n x dx. What do we want to do now? Switch sums. Fortunately, we saw a video earlier today about switching sums and integrals. We don't have time. It's going to be down to the wire. If you look at what's going on, we integrate from 0 to 1. Well, if m equals 0, we go from 0 to 1. Then when m equals 1, we're basically going from 1 to 2. This basically just becomes the integral from minus infinity to infinity of f of x e to the negative 2 pi I n x dx. Is that it just boom, 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 it all puts together. Aha, and that's our definition of f hat of n. So this then becomes the sum n less than or equal to n of f hat of n. Now you let big N go to 0, infinity, did it, 950, done, Poisson, okay? We made it, okay? This was a lot of stuff, okay? We now have the Poisson summation formula. On Monday, we will look at consequences of stuff like this, and we'll actually evaluate the sum of 1 over n squared. You should at least see in your life once that is pi squared over 6. Okay.